Hello class, this is Professor Finan. So for part 3 of this course introduction, let's revisit our regression model hierarchy. So now we're going to kind of more formally define each one of these major categories of regression models. Linear model, nonlinear model, non-parametric regression models. So let's jump ahead. Okay, parametric models. So the first major type of parametric models is the linear model. And so linear models are linear combinations of an assumed function. I'm gonna call it phi j of x, and x is bold here, so this is the multivariate case. So some assumed function phi of j of x times a parameter, I'm gonna use beta. So beta j. And the regression estimates the value of beta j, given the data set. And so in this situation, the reason why we call this a parametric model or a parametric regression is that we say the model is parameterized by the parameter beta, which here beta is a column vector from beta naught, beta 1, beta 2 to beta m. And so we can write our function y, our dependent variable y equals, it's some function of x and beta, which are both vectors. And so this is beta naught times phi naught of x plus beta 1 times phi 1 of x plus beta 2 times phi 2 of x plus ... beta m times phi of m of x. And so this is linear model because it's a linear combination of a fitting coefficient beta times some function of x. Okay, so it's a coefficient times some function. So in the previous example, we tried, like for example, the quadratic fit. That would be beta 1 times x plus beta 2 times x squared. Also, we had the sine function. We had a beta naught plus beta 1 times the sine of pi divided by 24 times t. And so these phis, as the analyst, you will have to assume some functional form. And so the most common type of linear model are actually polynomial fits. And this is actually related to Taylor series expansion, which we will cover in lecture 2. And so the most common type of linear model, we can actually assume the functional form of phi naught, phi 1, phi 2, etc. And so phi naught, in almost all models, you should assume phi naught to equal 1. So basically, you actually have a constant. Beta naught is some constant, similar to a y-intercept in a simple linear model. And so then it would be beta 1 times x1 plus beta 2 times x2. This is for this example, let's assume that we have two input variables, x1 and x2. And so this is beta naught plus beta 1 times x1 plus beta 2 times x2. So this actually defines a plane. So if we eliminate the rest of the equation, this is a first order polynomial fit defining a 2D plane. But we can keep adding on more terms, the higher order polynomial. So beta 3 times x1 squared plus beta 4 times x2 squared plus beta 5 times x1 times x2. So this term right here is important because it's an input parameter interaction term. So x1 times x2, this is an interaction, the interaction term. And so especially for the multivariate problems, you might have two input parameters. So the output y is correlated to the interaction between two variables. Okay, so then plus beta 6 times x1 cubed. So this is the third order polynomial plus beta 7 times x2 cubed. Now there would also be the interaction terms. For example, there could be beta 8 times x1 squared times x2, okay? And then beta 9 times x1 times x2 squared. So to have the full expansion, you would include all of these interaction terms. Okay, now we have our fourth order terms, beta 10 times x1 to the fourth power plus beta 11 times x2 to the fourth power, and you could actually go on to infinity, to the infinite number of the higher order polynomials. And the reason why I gave this example is because these linear parametric models, or these polynomial fits, they have actually been used since the early 1800s in regression problems, and actually mostly started in the biology and agricultural sciences. Especially in the 1800s, there was the agricultural revolution, especially the development of fertilizers, and there was a lot of major improvements in agriculture in parallel with the Industrial Revolution in the 1800s. So actually a lot of the early regression theory came out of biology and the agricultural sciences. And the reason why they've used these low order polynomial fits is because there's closed form analytical solution exists involving a matrix inverse. So when you want to learn the values of beta from your data set, we can do this. There's an analytical solution that you can actually do it by hand. So in the 1800s, they didn't have calculators and personal computers. So they had to do these matrix inverses by hand. And so if the data set was small and you had a small number of parameters, usually you would use low order polynomials, maybe with some of the one or two of the low order interaction terms. And so we're actually, this matrix inverse, this is what's called linear least squares. We will cover that in lecture 3. We'll do the derivation and some example problems. But luckily, we no longer have to do it by hand. We can use your scientific computing software like MATLAB and Python. You can do matrix inverses for very large matrices quite readily with using the scientific computing languages. Yeah, and so historically, we would have our regression models would be limited to kind of what I wrote here. So usually limited to about the fourth order fit with then a limited number of the interaction terms. And actually, this type of model is quite for a defined input space that is relatively well behaved. There's enough flexibility in this type of low order polynomial fit that it's actually a quite flexible model. Okay, simple linear model. And so a lot of students get confused. We say this is linear regression or a linear model. There's also, so do not confuse a linear model with what's called a simple linear model. So a simple linear model is just the line of best fit for the bivariate case. Okay, so y equals ax plus b. So the line of best fit. So here it's equals beta naught plus beta 1 times x. So the simple linear model, which is also sometimes called the line of best fit or the first order or a first order polynomial fit, it's a particular linear model. Okay, so it's a specific type of linear model, and so and so if you're in a multivariate input space, the first order polynomial fit defines a plane in 2 dimensions, or if there's more variables, these are hyperplanes. So in this example, if we truncate this polynomial fit right here, beta naught plus beta 1 times x plus beta 2 times x2, that's a 2D plane. So this would be this is a 2D plane. But if it's a bivariate case, y equals ax plus b, that's a line of best fit. So that's called a simple linear model. So all simple linear models are linear models, but not all linear models are simple linear models. And so once again, linear, the word in linear model, it's a linear combinations of the coefficient times some function of x. Coefficient plus coefficient times some function of x plus coefficient times some function of x. It's linear in the coefficients. But the reason why sometimes this is confusing because many fields of research, especially in the social sciences, are looking to identify the correlations, so the positive or negative correlations between two variables. So the simple linear model is the default linear model. So in many fields of research, the simple linear model essentially is the default model that they will fit to their data. And so sometimes they will call it linear model. But for the general case, we need to distinguish between a linear model and the simple linear model. Okay, nonlinear model. And so nonlinear models, and this is a general statement, appeared after the 1950s. And this is when computers became available, especially in certain industries, such as the aerospace and the nuclear industry. So, for example, all of the development of jet airplanes and also space travel, satellites, sending astronauts into space, and also then nuclear weapons programs and also nuclear reactors that were being developed in the 1950s and 60s. Some of those first, large mainframe computer systems. It was these aerospace and the nuclear industries were some of the early industries that have access to computers. So we started seeing nonlinear regression models in the 1950s. And so nonlinear models imply that the fitting parameters of the functional fit, y equals some function of x and b, our input parameter vector and our fitting parameter vector, they appear that the fitting parameters beta, they appear both inside the functional forms as our phi's. Our phi of j is a function of x, but also in this case, a beta j. And generally, they will also have a linear coefficient. And so let's look back. This is an example of our linear model, beta naught plus beta 1 times x plus beta 2 times sine of x, sine of pi x. Here we've hardwired the frequency of the sine wave. But if we do beta naught plus beta 1 times x plus beta 2 times sine of beta 3 times x, this fitting parameter beta is inside the sine function. So it's a nonlinear model because the beta 3 is inside the argument of the sine function. Another example of a nonlinear model would be beta naught times the exponential of beta 1 times x. So here the coefficient beta 1 is inside the argument of the exponential function. So this is a nonlinear model. And so that's the difference between the linear model and nonlinear model. In both cases, for these parametric models, and this is actually a weakness of the parametric models, is you as the analyst, we have to assume the functional form. So here we're assuming it's some coefficient times an exponential function. Here it's constant plus a simple linear relationship plus a sine function. You have to actually assume, you have to decide, I'm going to use this particular form. But to tell you the truth, nonlinear models are not used they're not that common as regression tools, because the nonlinear models, they do not have the explicit analytical solution. So you have to use the iterative or the gradient-based methods must be used to determine the fitting parameter. So it becomes a multivariate optimization problem, which there you have to have a lot of scientific computing and computer programming skills to solve for the parameters. And here, then you get into things like, this is essentially it's a multivariate optimization problem. So you also need to provide initial estimates of your fitting parameters. And because if there's some problems, there might be local minima and maximum. So these gradient-based optimization methods, they will sometimes converge to a local minimum or maximum. And so there's a lot more, the nonlinear, in practicality, nonlinear regression is a much more difficult just from the practical aspect. So in industry, and then we'll give you some examples on the next slides. There's many examples of nonlinear regression models. So for example, in mechanical engineering, heat transfer correlation. So there are many, mostly in the mechanical engineering fields, there are researchers who do the heat transfer experiment, measuring heat transfer coefficient values for different flow regimes and different heat transfer fluids and in different surface geometries. And so most of these heat transfer correlations are developed from nonlinear regression. Also so I'm a nuclear engineering professor, and so one of the earliest applications of nonlinear regression was in the 1950s for determining the 6-group delayed neutron constants. These are the abundance and half-lives of the delayed neutron precursors used in the nuclear reactor kinetics. And so let's move to the next slide. Let's just look at, so here's an example of a heat transfer coefficient. So this is a kind of a common one. It's called the Churchill and Chu correlation. It's correlating equations for, I think this is from 1978, correlating equations for laminar and turbulent free convection from a horizontal cylinder. And so basically so here's like a cylinder, they did flow over laminar and turbulent free convection flow over cylinders and measured the heat for different heat transfer conditions, and they developed correlations. And so here it's a Nusselt number correlation, so it's 0.36 plus 0.518 and times. So this is the Rayleigh number divided by 1 plus 0.559 divided by the Prandtl number raised to the 9/16th power. All of that in brackets to the 16th power, and all of that to the 1/4 power. So all of this would be your beta naught, beta 1, probably beta 3, beta 4, beta 5, beta 6. So all of these strange numbers, and all of these exponent numbers, okay, these would all be determined from the regression, from the nonlinear regression. And so here they're actually showing here that these are the different data points from different actual physical experiments. And they say here, usually I think it's the author name. So they were aggregating data from many, many experiments. So for example, Koch did an experiment in air, using air as the fluid. Arton and Kilgore in air, Rice in air, Wamster in air. Here's Davis and toluene, which is an organic fluid. CCl4, so carbon tetrachloride, and aniline olive oil, and glycerin. Here's Schultz with copper sulfate and with hydrogen sulfate. And then Kudrlij, that looks like, I can't read it, and then Collins and Williams in air. So they collected different data points for different experiments. And then here they actually did 3 different regressions. You can see they're using different coefficient values, but also different exponents. So here's to the 4/9, here's to the 16/9 and the 1/6. So they have actually they have 3 different curves here, 3 different regression fits to this data set. And they're plotting it versus, this is the Nusselt number, the square root of the Nusselt number minus 0.6. And so here's an example of nonlinear regression. And so also another example from the nuclear industry is the measurement of delayed neutrons and the delayed neutron 6-group data, so the abundance and effective half-life. And so this is the famous experiment done by Keepin at the Los Alamos lab using the Godiva critical assembly. This was done in the early 1950s. And so here they're assuming a functional form. Y equals, it's a summation, and usually from J equals 1 to K. K is usually 6. Sometimes we use 8. But aj times the exponential negative lambda j times t. And so the aj and lambdas, those are the fitting parameters beta, which they fit to the data. And they developed nonlinear least squares, or weighted nonlinear least squares. So weight, WNLS, weighted nonlinear least squares. And this is showing the data points there are the actual measured count rates. This is count per second. They were actually measuring neutrons that were being emitted by the fission products from the fission of the uranium, plutonium, and thorium isotopes. And so they fit. These are these exponential curves. And they're using there are three different axes here. Okay, that's why there's three different curves. And there's three sets of axes on these figures. And so they use weighted nonlinear least squares to determine your parameter A's and your lambda parameters. And so those are some examples of the nonlinear regression. And so now let's briefly discuss some of the issues with linear and nonlinear parametric regression models. And so when we do regression, we should be primarily concerned about accuracy. And when I say accuracy, there can be the statistical accuracy, and also we want to know the accuracy, just how does the model match our data points? But remember, these data points, each one of these data points are random variables, okay? When they did this experiment and obtained this particular data point, if they repeated the exact same experiment, they repeat the same experiment many times in the exact same conditions, they're actually going to get a spectrum of data points. And so remember, these are a random variable. And so how well does the model reproduce the existing data set? That's more of the statistical accuracy. But then what we should be concerned about, how well does our regression model predict the true underlying physics? And so both of these elements of accuracy are conditional on the assumed function form of the regression functions phi of j, or in the nonlinear case, phi of j of x and beta j. And so, for example, and this is the delayed neutron problem, they assume that it follows the radioactive decay law, which for most radioactive substances, this is the correct formula. But actually, in reality, for some of the fission products, they're in complicated decay chains. So they're what are called parent-feeding effects. And actually, no one in the nuclear industry has quantified the parent-feeding effects for the 6-group parameters. And actually, it's significant for the group 6 and the group 5 neutrons. And there's actually bias in this experiment that has not been quantified. And so the accuracy is really going to be on how close does this assumed functional form. And so here in the heat, they assume this Rayleigh number divided by this ratio of the Froude number raised to all these exponents. So it depends on how well does the equation, the form of the equation you chose, how well does that represent the true underlying physics? And then model flexibility, the second bigger point. So if you have just the wrong functional forms, you're not going to have a good model. So if you're using the wrong functional form that doesn't agree with the underlying physics, your regression model, the regression, you can perform it correctly and actually and correctly estimate those parameters, beta naught, beta 1, beta 2, beta 3. But if the functional forms are not accurately describing the underlying physics, you might end up having a model that has very poor predictive accuracy. Also, the second issue is as j becomes large and or the theta j becomes flexible. So think of the sine and cosine functions in the Fourier series expansion. So if you keep adding more parameters and more functions like sine waves with different frequencies, you can start to, your model becomes very flexible and starts to what's called as overfitting. It basically, the regression model seeks to achieve perfect agreement with the training set. Okay, so if we add too much detail into these regression, if you have, for example, if we keep expanding this polynomial fit way out to very, very high order terms, now you're going to start, instead of finding the underlying kind of smooth relationship, you're going to be fitting to the data point, fitting to the noise. And that's a serious situation called overfitting, which you need to avoid. That's probably one of the biggest problems in regression is overfitting. That's one of the huge problems. And so if you have too many parameters or too flexible of regression functions, your model is going to be prone to overfitting, which is a terrible situation. And so if you have an overfit model, the regression model is worthless. Actually, it's not is it worthless, it's actually, it gives you the wrong information. So it's like negative. It actually so it's worthless implies zero. It's actually negative. And so the regression model is worthless and gives wrong predictions. And this is possibly of large magnitude as well. And so you could be off by a factor of 10, 100, 1,000. The regression model, not only will it not give the accurate solution, it could give a very, very wrong by orders of magnitude. And this is as soon as the prediction point deviates from a training point. And so when you're near one of those sampled data points, the model converges to the data point. And so let me just give you an example of the overfitting. So let me put up the screen real fast. So an example of overfitting. This is our simulated data set example. If you did some very high frequency sine waves or supposition of sine waves, trying to, this would be an example of, and this is actually what overfitting looks like. And what happens with overfitting when you're in between data points, the model will extrapolate way off scale. And so when you're, if you're in between these data points, the model will give a crazy prediction. That's not unphysical. So if you see a regression like this, 98% of the time, this is an overfit model that is bad. But now, unless you know that you're looking for high frequency signals that are embedded within other signals. Okay, for example, in signal processing electronics, you might actually be doing this. Is this just random noise, or is there a true high frequency signal embedded within these other signals? So that's called signal processing. So here you would have to be very careful. It depends on your application, but generally you need to avoid overfitting. Let me erase. We're talking about issues with a linear and nonlinear regression. Yeah, so you need to avoid overfitting, especially the AI, the artificial intelligence, machine learning. They are very prone to especially the Gaussian process models and the artificial neural networks. They are also very prone to overfitting. And that's why you always need to have what's called the cross-validation set. a set of independent measurements that are not used in the model training. Because an overfit model will then give poor predictions for the cross-validation set or the test set. Yeah, and so if we do a model that's too complicated with too many parameters, too many regression functions, on the other hand, if a too simple of a model is assumed, then the interesting underlying structure is averaged out. So for example, if you just assume y equals beta naught, the sample mean, it is a somewhat accurate model, but you've lost all of your detail. And usually we're doing the regression to learn something about the underlying physics. What is the underlying functional relationship between X and Y? So that's sort of the point of doing the regression, is to learn the actual functional formula, gain insight into the functional relationship between variables. And so if we have too simple a model, we lose that detail, and that's why we're doing the regression. And so this is another type of model that will often occur, is what's called the uninformative model. And this is when the regression function returns the sample mean of the training set. Especially I've encountered this in my own research with the Gaussian process model, and I recently saw in a PhD defense for the artificial neural network. Sometimes those models, they just return the sample mean, and that's the uninformative model if the training isn't done properly. And so that's the other. So an overfit model and also uninformative models aren't very useful. But in the absence of any other information, the sample mean is sometimes the best estimate or the best unbiased estimate of Y. If you don't have any other information, just the sample mean is actually the best estimate. And this is something, so I know a lot of you might be trying to use the AI and the machine learning. Something you need to watch for. The improperly trained AI machine learning models will often return the sample mean or be overfit. Or they might be overfit near the data points, but then when you get away from the data points, they return the sample mean. If you have a mismatch between an assumed theta, or an assumed regression function theta, and the underlying physics, this can lead to the bias in some regions of the input space. Okay, and so you might have a regression function that works really well for a certain region of the input space, but then breaks down in others. And so, in fact, let's go back to this example. It looks like there's the three curves. There's this curve here, which I think is this top equation. Obviously, in this range of numbers, it is not agreeing well. But it might agree. I think, which one is this? This was an old paper, so it's a little bit hard to distinguish the lines. But obviously this correlation does not work well in this range. But it might have high predictive accuracy in a different range of values. So that's another thing you have to look out for. Yeah, so this mismatch can be localized in certain regions of the input space. Okay, also another just general issue with both the linear and nonlinear parametric regression, but also the non-parametric regression, the AI machine learning, is most regressions will have poor performance or be unstable, or have the unstable solution near the boundaries of the input space. Okay, And one physical explanation for this instability near the boundaries is what's called high leverage. And we're in lecture 6, we're going to discuss this leverage and least squares regression. Okay? So high leverage of the outline predictors and linear least square regressions. And so in many practical examples, and I have had to do this in my own research, is you need to implement stabilization workarounds for the boundaries of the input space to stabilize the regression function. And to summarize the parametric regression models, and this is what you need to, as a student or a young researcher wanting to do regression properly and apply it to your research, is you need to remember there's always a balance and a trade-off between simplicity and complexity. Okay? We want to have generally the more simple. Sometimes y equals beta, y equals a constant is the best model. So you always want simplicity, but you also want to capture the underlying physics, which might, in some applications, this can be complex. So there's that balance and trade-off between simplicity and complexity. And so in this course, we will teach you some tools that are useful to assess this balance and trade-off. And one of the most practical, one of the first things you should do is what's called residual analysis, which is the topic of lecture 4, and cross-validation, which are both practical, what I call offensive and defensive tools in addressing these issues. So cross-validation will help determine if you have the overfit model, and also the residual analysis will tell you about the uninformative model and also overfitting. And so, and this residual analysis and cross-validation, in this lecture, we're going to be doing linear regression examples, but you should do the same. The procedure is the same whether you're using nonlinear regression models or if you're using the non-parametric regression and the AI machine learning. And so the tools in this lecture, in this course, we're focusing on linear regression because probably about 80% of all regressions are linear regressions. But the machine learning is becoming more popular in the recent years. But these tools and these procedures can be applied to any regression. But we will just use linear regression as examples. The final topic is, let's talk about non-parametric regression. So we probably, in this course, we will not cover the non-parametric regression. Maybe next year we will have we'll extend this course to include the nonlinear regression with gradient-based methods and non-parametric regression. So non-parametric regression, it's where the functional form of the regression model is learned from the data. And basically, as an analyst, we make minimal assumptions are made about our phi of j, the functional form of the regression. And so basically, these non-parametric regressions perform data smooths or very local regressions in the input subspaces. Most of the AI and machine learning algorithms can be classified as general multivariate non-parametric regressions or data smooths. But the one drawback of non-parametric regression is you will generally require large training data sets. So you need large data sets because we're not making assumptions of the functional form. You need large data sets, training sets. And also we still have the issues of overfitting and uninformative modules. Okay. The last topic is also just some other terminology. In this class, we're calling all of these models regression models. But in the other fields and areas of research, a regression model is called by a different name. So the term regression model varies significantly with the field or the application, but the general definition holds. It's a predictive model to give hopefully accurate estimates of y given x for the full range of x. And so another common terminology is called a response surface. And then in some fields, these response surfaces are explicitly assumed to be represented by the low order polynomials. Okay, but it doesn't, you can build a response surface with any regression method, just especially from the structural mechanics. Back in the 60s and 70s, they started doing response surfaces. So like they were usually using the low order polynomials, but you don't have to. Also, in the engineering fields where you're using computer simulations, these are sometimes called a code surrogate. And so a surrogate is something that replaces something else. And so a code surrogate is usually meant to be a fast-running alternative to an expensive, complex computer model. And so, for example, in the auto industry, but also especially for the aerospace industries, you might be doing very large CFD models of the shape of the airplane wing. And so these large CFD models take very, very long simulation times and also a lot of large computational power. And also in the nuclear industry, we might be doing what's called full core Monte Carlo simulation of a nuclear reactor core. So these are like high fidelity models, high precision, lots of detail, but very slow. It takes a long time and you have to use supercomputing architectures. And so if you can do a limited number of forward runs with the expensive models or with the large CFD or the Monte Carlo, you can then generate the training set and then perform a regression to come up with a regression model, which we call a code surrogate. And then for other types of calculations, you can directly use the code surrogate. So you can do a much larger number of simulations in a shorter amount of time. Also, meta model. Meta model is another terminology. Also, a correlation. So especially in the heat transfer, pressure drop, in the thermal hydraulic fields, a correlation is essentially a regression model. Another interesting subset of regression models is depending on what information does the end user need. And so sometimes we don't need the explicit mapping from y equal to some function of our multivariate input space x. We might, some regression applications is classification. We want to know plus or minus A or B. We want to classify areas of the input subspace. Okay, so for example, in the medical imaging processing, so for example, we have the different, there's like the MRIs, CAT scans, there's all these different medical x-rays, medical imaging technology. Let's say you're looking for cancer tumors. And so in the medical image, maybe there's some sort of, you can see that there's some sort of mass on the image. You want to know, is that a cancer tumor? Is it not a cancer tumor? And so, so that's an example of classification. Also, there's another concept called a limit surface. And this comes out of the reliability engineering fields. And it really has its start in the structural mechanics and civil engineering. Basically, they want to know if you're building, let's say, a bridge or a tall building, and you're under, let's say, an earthquake. And so that you're having some structural stresses applied to this structure. What combinations of different variables, inputs, will the structure fail? So this comes out of reliability engineering. It's called the limit surface. The limit surface, which I'll call LS. And this is where you define a new function g of x, which equals our f of x minus some threshold value, or I'm going to call it YL, L for the limit. And then you set this equal to 0. And what this does is the limit surface partitions the input space into success and failure regions relative to a response threshold YL. So for example, above and below this surface, or to the right or to the left of the surface, might mean failure or success. And some fields, especially in the structural mechanics, some fields will assume the surface is represented by low order polynomials, but once again, it doesn't have to be. And so if your goal of your regression is to obtain a limit surface, the regression model only has to be accurate near the surface, not over the whole range of predictors. Then this effectively reduces the dimension of the input space. And so, so here you would seek accuracy near where f of x only needs to be accurate near y of L. And so, for example, in the nuclear power plant safety analysis, we have a parameter called peak clad temperature, or PCT. This is the maximum temperature of the metallic zircaloy cladding. So in the nuclear reactor, we normally have little uranium oxide fuel pellets, but they are stacked up in a thin cylindrical rod. And the most common type of, it's a metal called zircaloy, it's a zirconium alloy. And so the fuel rod is this zirconium alloy with the fuel pellets inside. During an accident, the fuel and the fuel rod will heat up. And there's a limitation. The maximum temperature of the zircaloy cladding, it needs to be less than 1,477 Kelvin. This is the regulation. And because above this temperature, there are exothermic water-metal reactions occur. So the zirconium metal exothermically will react with the water and steam. And then that actually creates the hydrogen gas and more energy. And so sometimes when we do the safety analysis, we want to know which type of accidents will lead to clad temperatures near 1,477 Kelvin. Because this is the difference between an accident that you can recover from versus a severe accident where you will have fuel melting and release of radionuclides, and usually the loss of the reactor. And so here is an example. This is a computer simulation. This is a nuclear engineering example. This is the peak clad temperature limit surface. And this is for a large break loss of coolant accident for the OPR 1000 reactor, which is about 8 or 9 of these reactors operating here in Korea. And so the loss of coolant accident is when there's inside the nuclear reactor, we have many large reactor coolant pipes. So basically, there are large diameter pipes where water is being circulated. And so if one of those large pipes break, we call it a large break loss of coolant accident. So you're losing water from the nuclear core. And so what happens, and so this is actually computer simulation data. This is time versus the clad temperature in Kelvin. And these are many different simulations performed with different input parameters. And you can see that the temperature, the time-dependent temperature, it follows different trends. So all of these ones, the temperature, it reaches a maximum of 1,100 Kelvin, but then the temperature decreases and then stabilizes. Where in other sequences, the temperature increases and can actually exceed the regulatory limit. And so in these simulations, here are some more examples of simulations. And so these simulations are actually done with the MARS code, which is what's called a system thermal hydraulic code used for the nuclear reactor safety calculations. And so this is it's computer code, computer simulation data, which provides the training set for the peak clad temperature as a function of 3 input variables. So this is sort of the raw data. And so we take each one of the maximum temperatures from each simulation as a data point. And so here is an example of the response surface, okay, and then the limit surface. And we've had, actually in this example, we have 3 input variables. One is the pump delay time. So in the nuclear power plant, we have then, if there is a loss of coolant accident, we have large pumps that will turn on and will pump extra water into the core. But there's different combinations of those pumps. So there's the pump delay time is the amount of time it takes for the pump to start. And so actually there's something called the emergency diesel generator. They have to start to create the electricity, then to provide electricity to the pump. The pump has to start pumping the water. And so there's a delay time. There's also then the safety injection mass flow rate in gallons per minute or liters per minute. And so that's the actual flow rate of water provided by those pumps. And then there's something called the RWT, the refueling water storage tank, water temperature. So that's the temperature of the water these pumps, the pumps are providing cold water to the core. And so there's 3 variables. This is the actual response surface done. This was actually using a Gaussian process model for the regression. So this gives the peak clad temperature from the 1100 all the way up to around 1550. So going back, this response surface, see, here are the 1100 Kelvin. We have that's the peak clad temperature. So this surface tries to predict all of the maximum points. And you can see that it's this kind of, and the blue dots are the actual simulation data. And so some of the dots are below the surface, some of them are above. But it's sort of it's a relatively smooth surface, but it is sort of non-linear. Okay? But with the limit surface, our 3 axes, this is x1, x2, x3. And basically what this surface represents, if we take the 1477, which is, it's sort of an arc, okay? Let me put the screen up and I can draw. So, on this response surface, the limit surface is the 1477, which is sort of that red color, so probably this arc is the limit surface. But we're only in 2 dimensions. Here we're holding the 3rd parameter constant, okay? So you can see here, basically these 2 curves match. So this is the pump delay time and the mass flow rate. And so this is the pump delay time and mass flow rate. And so here we're mapping this limit surface, but now we're doing it on the 3-dimensional plane with the function of this 3rd parameter. So we build the surface, okay, at the combinations of these 3 variables. So now everything below, any combination of these 3. And this is, okay, x3, x1, x2. So any combination of these 3 variables that's below this surface, this is a success. The nuclear power plant did not melt down. Anything above the curve is the failure region. So there's going to be a meltdown. And so here, so the limit surface concept, it's a special case of a regression model. Okay, and it has some practical use in several different engineering fields, mostly in the reliability engineering. And actually, and I've personally done these are some figures from a paper I wrote. So I have personally done some work in this area. And I think I was using the Gaussian process model for regression in these particular examples. And so this is just to give you some information on other applications of the regression. Okay, so a few more things I want to touch upon. So let's talk about extrapolation weakness of most, if not all, regression models. And so as scientists, engineers, and researchers, especially when we get into the machine learning and AI, we sometimes lose focus on the big picture. And generally when we perform research, we're trying to learn about physics, the natural environment, biology. We're trying to learn about some process. But we start using computer models, regression models. We start to get very involved in the methodology rather than the end application. And so a lot of times we become overconfident in our computer model. So if we're using, for example, CFD, computational fluid dynamics, we think we're getting the correct answer, the true answer. And so a lot of engineers and researchers and scientists, we get too involved with our models and not concerned about the true underlying physics. And so many times researchers will give a too high of confidence in the accuracy, the predictive accuracy of either their actual computer model or their regression model. And so one word of caution is generally regression models are poor or terrible extrapolators, okay? And so if you try to apply that the regression function, so let's go back. There, x is from 0 to 1. If we fit a regression function, that function can go into the negative. It can also go out past 1. It will give, like if we did some sort of sine wave, it will then keep going, okay? Or if we had for example, we just did a simple linear fit, the linear fit will keep going out of the frame. It will keep increasing. So the regression model will give you an answer, but it's outside of the range of your sample data. And so you need to be very careful if you're using your model in an extrapolation. You're extrapolating outside of the boundaries of your data set. Okay? And so, but in some situations, if you knew something about the underlying physics and you program that into your regression models, and if the underlying physics are simple, okay? So if the underlying physics are simple and known a priori, and you've built those into the model, you can sometimes use your regression model for extrapolation. And so generally, regression models are better for interpolation. And so in some areas, I'm going to give you a couple examples. So in particular, time series forecasting. So sometimes the X variable is time. It can go back, days, weeks, months, years, sometimes even centuries. And so people develop what are called time series forecasting. Forecasting is predicting into the future. And so they build essentially a regression model that is back tested on the historical data. And so we have the historical time series data from the time before. And so we perform regression on the historical data. It predicts the historical data well. And then we apply that predicting into the future. But generally, these time series forecasting models will break down when the predictions into the future encounter basically new explanatory variables. And the best way to explain is to give you some examples. Let's say you work for a hedge fund. Okay, you're trying to do investing and speculating and making large profits in a short amount of time. And so you want to predict the prediction of the oil price using a model that's back tested from 1975 to 2018. And we're going to use this model to predict what will the price of oil be in 2023. And so let's think for a second. What would be an issue with this model? Do you think a model back tested on the oil price data from 1975 to 2018. I mean, that's a long period. That's almost 45 years of data. Will that model do you expect that model to give us an accurate prediction of oil price in 2023? And what are some issues? One is, when did they start the back testing? 1975. Now, probably most of the students, if you're a student watching this video, you probably weren't alive then, but in 1973 was the first oil embargo. And so in 1973 to 1975, there was a giant massive disruption to the oil market due to the first oil embargo. Okay, and so the back testing, the range of the back test kind of was a little bit biased and actually missed a giant event that had huge influence on price. Also, 2018. What happened from 2018 to 2019 to present day? There was the China virus, and the world economies were shut down. And still, like for example, China, which is the world's second largest economy, half of the country is still in lockdown, and I think it's September 12th, 2022. So there are still huge in the oil market, the world energy market. There are huge disruptions going on currently, and so probably a model that was developed in regression on this historical data in this range is probably not going to be able to predict coronavirus, the war in Ukraine, all sorts of technology changes. Okay, so you need to be cautious. Okay, when you're doing prediction. Also, for example, another giant failure of regression models is the climate change models and large complex computer models in general, which the climate change models have been always back tested on the historical climate data. And so almost none of the climate change models have made predictions. Now we have a decade of, back in the 2000s and early 2010s, a lot of predictions were made with climate change models, and none of those have really come true, or in very rare instances. Most of them have been completely wrong. And so, so always be careful if you use your regression model for extrapolation. And just remember, this was about extrapolation, but also remember most regression models, including artificial intelligence, perform poorly and/or are unstable near the boundaries of the input space. And so those are just some of the things you need to keep in mind. So this is the end of the introductory lecture. In lectures 2 through 7, we're going to start to hit on mostly key mathematical concepts. And in each module, in each lecture, we'll have a MATLAB programming exercise where we'll develop a simulated data set and actually perform regression on it. And we'll visualize the data using plotting. So not only will you learn about the linear regression and then how to assess your regression model after you've constructed it, you also can learn some basic computer programming skills and also data visualization. And so that is it for lecture 1. And we will continue on with lecture 2 next time.